Hi, welcome to Lecture 9 in this series for an Introduction to Proof course. Today I'm going to go through some stuff about the conditional statements. The basic layout is we'll talk first about conditionals, then biconditionals, a couple of other types of statements that are related to the two of those, and then finally the relationships between all those statements we're talking about today. So let's get going. Remember back in the section on algorithms, I told this joke where the punchline was, well, not the punchline, but the setup was if they have eggs, get a dozen. When we're talking about algorithms, if A then B, that kind of construction, that was designed to say, you would do different things depending on the value of a Boolean. So if A then B meant you'll do B, depending on A. A is an if that, A is a Boolean thing, a true or false item, but B is something you might actually execute. For instance, if the second input is 0, print an error message and exit. Right? So the thing in the if part of this sentence is a question that you could answer yes or no to, a true false thing. The rest of it, though, is instructions for doing something. We're doing something different now. We're in logic, and so both the A and the B are going to be statements. They're going to be things of a Boolean character. And really, the way to think of this is the symbol we're going to use, which that's it, the little arrow, is a way to hook statements together to get new statements. So yeah, the result, A funky looking arrow to B must be a Boolean thing. The result of this has to be a statement too. I should say must be. We want it to be, right? We want it to be a new logical statement. So it's going to be either true or false. There's some terminology we should learn. The statements on either side of the arrow do have names. We always call A the antecedent. This is in the case that it's A implies B. Many people, me included, call it the if part. That's fine, but you sound more sophisticated if you say antecedent, don't you? B is known as the consequent, and me and many others would call it the then part. It also sounds better if you refer to the entire thing as conditional. Don't say an if-then sentence. Say conditional. That one I agree with. Saying conditional is not too much extra work, and it does make you sound more grown up. I actually slipped and used this word when I first pronounced this arrow up here. I said the implies arrow. Well, the word implies is a direct substitute for the arrow. So if you say, I don't know, if it's raining, there must be clouds in the sky. That would be if raining, then clouds in the sky. Yeah. But you could just as well say rain implies clouds. Rain. Yeah. All right. So I don't think I need to beat that one too much harder. When you have a true conditional sentence, one way to think of it at least is that truth of the antecedent is going to force truth of the consequent. I literally often do this mental conversion when I'm looking at something that looks like A implies B. I say, all right, when A is true, it's going to force B to be true. I have a little truth table here. A, B, those are the columns for A and B are filled out. The columns for A implies B are not. Why not? Because I wanted to do them one at a time, basically. The first line is very obvious. If the idea of the arrow is that it says the first thing forces the second thing to be true, and both the first thing and the second thing are true, then the arrow is certainly not lying. And I think this spot is quite obvious too. So if the arrow is supposed to be telling you that when A is true, B is going to be true, and A is true and B isn't true, you've got a problem, right? So in that case, the arrow is a liar. We say the implication, the implies arrow is false in that setup. What do you do with the rest of it? This is troubling to a lot of people, but this is what you do. You make them both true. And why? Well, because the arrow says that if A is true, it makes B be true. What if the A is not true? Doesn't say anything about that scenario. It's sort of like you want to give it the benefit of the doubt. If A isn't true, then you just sort of say, all right, I'm not going to call you a liar over that. What other statements would have the same truth values as A implies B? Well, that's a good question, because can we say that A implies B in a different way? Maybe the title of this slide tells you that we can. The easy observation to make is that there's 3 T's and 1 F in that truth table. Should I go back? See, 3 T's and 1 F? T there, T there, T there, a single F. Okay, so of the other things we have, ands and ors were the things that gave us a 3T, 1F pattern. Of course, it's definitely not just A or B, because that one would have the single false up in the very top row, right? A or B. That's not true. It would have its one, not in row 1, but in row 4. But anyway, not in row 2, which is where we'd hope it to be. Well, we did this sort of thing in the activity for lecture 8, so I won't hold you in suspense. It's this. It's not A or B. No, I really think we should go back and look at the truth table again. You see that if we were in this second row and you put a not on the A, then the T that's here would become an F. You left B alone, and then you ORed them. That's where you'll get an F. So again, this is the technique I talked about for OR statements. Just concentrate on the row where it's going to be false. And not A or B will be false right here in row 2. Everywhere else it'll be true. Okay. Have you ever heard people use the word or when they're issuing a threat? Saying or else, right? Usually threats, though, are if-then sentences of some sort, right? If you do or don't do something, then some consequence is supposed to follow. But here's an example. A parent might say to their teenage kid, if you stay out past 11, you'll be grounded. Could they say this too? Get home by 11 or you're grounded. It's kind of a mean parent. I think 11's a little early, but whatever. The first of those is certainly if A, then B, right? If you stay out past 11, then you'll be grounded. A is the staying out late, B is the getting in trouble. The other is of the form not A or B. The B in both of these is the same. It's grounding, right? But the A is staying out late. So the not A is getting home by curfew time. Okay, so finally, last little piece I want to mention while we're talking about conditional sentences is a name for that scenario where the bottom 2 rows the A was false. It's called vacuously true when the if part or the antecedent is false. And in that scenario, when the antecedent is false, you don't even care what the truth values of the consequent are. It's immaterial. We're talking about those bottom 2 rows of the conditionals truth table, provided we're talking about the regular A implies B conditional in the truth table as I've set it up before. Because, just like with ands and ors, you could put negations in front of A or B and change how things looked in terms of the order of the truth table. The thing that people miss about this notion of vacuously true is how powerful it can be. I have a colleague that complains sometimes about students never notice that they can prove something vacuously. So please be one of the students that shows this guy that's not true anymore. Be conscious of this. You can prove that an if-then sentence is false, is true, just by showing that the if part never actually occurs. It's never the case that the if part is true. So if the if part is always false, the thing is true just because of vacuous reasons, which is fun. It's really kind of neat to prove something difficult by just showing something very simple. Okay, our next section is about biconditionals. As you can probably tell from the word by, the word part by in there, that it's about two conditionals. Here's the two. We'll often write this actually. A implies B and B implies A. But that's a little bit wordy or symbol-y. So you can write this two-headed arrow in between A and B if the implication works both ways. Oh, speaking of the implication working both ways, throughout my book and throughout these slides and the videos, I'm using the implication arrows only going left to right. And that's just personal preference. It's okay to write them the other direction. So it's maybe not as commonly done as left to right arrows, but you could have right to left arrows for, you just, then the role of antecedent and consequent is switched too, right? So don't mess up that. But anyway, the two-headed arrow means both that A implies B and B implies A. So the name for that is biconditional. I think that makes sense. It's a conditional that goes bidirectionally. Yeah, right. We've seen this symbol before when we were doing definitions. I used the phrase exactly when in definitions, but we then fairly quickly turned the words into that double-headed arrow. So here's the truth table for the biconditional. I'm not sure what I have to say about this other than that it's true in the top row where A and B are both true, and it's true in the bottom row where A and B are both false. A way to paraphrase what the biconditional does is it tells you that A and B have precisely the same truth values. When it's true, A is either both true, A and B are both true, or they're both false. I think it might be wise for us to notice that people in general speak fairly imprecisely, whereas in math we're trying to get to real precision, right? So if it's really quite common for people to mean a biconditional, but just say an if. So suppose this is an example that's gone through quite a bit in the Giant book. I found it just, I guess, amusing to pose all this in terms of your mom talking to you. You can have dessert if you finish your vegetables. Now, that actually already gives you a way in which spoken ordinary speech is different from math. A math person would never say then if then that way. They would say if you finish your vegetables, then you can have dessert. The if part is supposed to come first, but in language we often just say the then part and then if and then the if part. So what did she mean if she said, I'm going to fix it my way. If you finish your vegetables, then you can have dessert. Look at the truth table up above us here. The top line is you finished the vegetables and she gave you dessert. So clearly her statement was a truthful one. The second line is you finished the vegetables and she did not give you dessert. Mom, what the hell? That's a lie, right? That's her if statement is false. The bottom has to do with vacuous truth. And the reason I like to bring mom up in this scenario is if you don't eat the vegetables, she said, you got to finish the vegetables or I won't give you dessert, but you don't. And she can either give you dessert or not, true or false in the B column. You can call your mother a liar. If you didn't finish the veggies, but she still gave you some dessert, I wouldn't call her a liar. I might call her soft, but not like she was a liar, because the statement was about what will happen if you finish your vegetables. And when you don't finish your vegetables, you're in that scenario where you give the speaker the benefit of the doubt. Probably, though, that's not what your mom meant, right? She didn't mean the difference between the biconditional and the conditional is this one symbol I'm trying to point out there to highlight. That would be a true if this was the A implies B arrow. but it's not. It's a false in the if and only if. And likely, this is what a parent would really mean if they said, finish your vegetables, you can have dessert. They mean, if you finish your vegetables, you can have dessert. And if you don't finish your vegetables, you're not getting dessert. Nobody's parents ever say, you can have your dessert if and only if you finish your vegetable. That's probably what they should actually say. I mentioned in the previous section about conditionals that there's a single word substitute for the arrow. You can say implies. And I just spoke the single word symbol for this double-headed arrow. It's not a single word, but it's said so often and so quickly that it runs together. If and only if, right? I almost think of it as one word. It's not. It sometimes gets spelled as one word. You can write IFF in, at least if you're writing to other math people and they know that abbreviation, IFF, or if and only if. But I've noticed that spell checkers don't particularly like that. Okay, so we're going to move on now to the series of other statements that are related to conditionals. The first one is, the title of the slide is converse, not an athletic shoe maker, but a type of logical statement. It's the second conditional that you see when you're looking at the if and only if thing. So yeah, if A and B is a given conditional, its converse is B implies A. There is a kind of a two-way street thing going on here, because if I converse the converse, I get back to the original, right? Because it effectively just means swapping the things on either end of the if-thens, excuse me, on either end of the implies arrow. So it's quite frequently the case that we refer to them both as the two things are converses. I think I put the emphasis wrong there. The two conditionals are converses. Accent on the first syllable. Darn, the joke is to say syllable right at that point. Okay. It's a common error. It really is a very common error to mistake a conditional for its converse. People mess this up all the time. When you really get a strong handle on which direction is the intended statement and which is the converse, you'll notice these things. So start watching out for it, the way people get these wrong. So here's an extended example. The predicates A, there's gas in the tank, and B, the motor runs. I'm actually thinking about a lawnmower here. So A implies B would mean, let's say it in words, if there's gas in the tank, the motor will run. That sounds reasonable, doesn't it? So I feel like you've got a good if-then there, a good conditional sentence. B implies A would mean if the motor runs, there is gas in the tank. I guess that sounds pretty reasonable too. Are they the same? That's really the question. And they're actually not. Think about this. If A implies B is sort of saying, I'm confident. I know that this lawnmower is in good shape. And if you pull the cord, it's going to start up. Great. What is B implies A saying? Well, that's actually much more about objective reality. It says that if somebody's already started the mower, you can hear it running, you know there has to be some gas in the tank. Well, yeah, unless it's electric or it's run by demons or whatever. So, assuming I'm afraid this is going to be old school and out of people's understanding in just a few years, when all the gas lawnmowers in the world go away, because everyone will have electric ones. But oh well. So here are the truth tables for a sentence. A implies B, a conditional sentence, and its converse, B implies A. I just filled them all out. I didn't want to do the dramatic reveal on this one, but we saw the conditionals truth table before. It starts with a true up top, and then the second row is where you get a false, because the if is true and the then isn't, and then the vacuous truth down below. Let's look at the rows where the other guy is vacuous. When is B implies A vacuously true? Remember, that means that the antecedent, which in this case is the second, or the B, that's when the antecedent is false. Well, I see those. That happened there and also here. So these two t's are from vacuous truth. Where's it? Where's it t for a good solid reason? Oh well, I've gone and advanced the slide too quickly. It's true for what I consider the right reason in the top row, just like the other one is. Both A and B are true. So if you think of this as B's truth forcing A's truth, then B's true and A's true. That the force seems to be justified. What was that thing I went back on? Notice that if we and the two of these, you're going to get the exactly when thing. That's actually what I started with, but notice, look at it again and see it. We've got the truth table for A. A implies B is true both in the top and the bottom row. So is B implies A, top and bottom row. And they're mixed up in the middle two rows. The first one, the original conditional, is false in row 2, and the converse is false in row 3. That means if you and those, the middle two rows are going to always have both a T and an F around them, around the and. So you're going to get false there. So the and of these two guys goes true, false, false, true. And that's the biconditional. That's what it means. Since we talked about a mistake in the last group of things, I've kind of mentioned that there's a mistaken idea about negation. A lot of people think, well, just because this is sort of the way algebra usually works. If I want to take a not on a minus sign on something like A plus B, well, I bring the minus sign in on both of them, don't I? It's like a distributive rule. So that it seems reasonable to think that the negation of A implies B would be negation of A implies negation of B. Well, that's wrong. That's just wrong. Why can I tell right away that that's wrong? The thing on the right here is an implication. Yeah, it's got minus signs or negations in different spots, but it's basically an if-then sentence with, things other than straight up A and B on the first spot and the second spot. If-thens are true most of the time because of vacuous truth. So whenever not A is true, you get two trues, and then when both not A and not B are true, you get actual truth, and there's only the one place where it's false. But if we're negating A implies B, this is something, A implies B is something, again, that's true in false in exactly one place. So when we negate it, we get something that's true in exactly one place. So the thing on the right here is true 3 times. The thing on the left is true only once. They can't be the same. Oh, I had a bullet for the point where I was supposed to explain why they can't be the same. Well, even though they're not the same, this idea of sort of distributing the not across the parts of the conditional is a common enough thing to see that people came up with a name for it. So it's known as the inverse. Or you can equally well say A implies B and not A implies not B are inverses of one another. While we're at this moment in time, I think just a little by the way thing, the inverse is not the right way to negate a conditional. So what is? Well, think about the truth table. Here's the truth table for filling out the columns for A and B, and also A implies B, as we've seen a few times now. So what is the negation of A implies B? That's not hard. Just you're going to take each T and make it an F, and each F make it a T. So it goes false, true, false, false. Perfect. There's one T, and it's in row 2. Right? So that's an and sentence. I already we did a bit of exercise with this last time. So that definitely is an and sentence, but which one? Which one is it? Okay, wait a minute. I've again advanced the slides too quickly. Sorry. Wow, I went really crazy there for a second. There's one T in row 2, where at that moment we're supposed to be talking. One T in row 2. I think I can say this. To get an and statement to be true, I need the things on both sides to be true. But in this row 2, A is true, so that's fine, but B is not. All right. So I just need to put a not on the B part, not on the B part. That is, A and not B is the negation of the if-then. A implies B. Yeah. Which and sentence is that? It's A and not B. Calling out BS. I decided to strike that out and say just calling out an error. It's calling it out when somebody uses an if-then and then it turns out they were wrong or they maybe intentionally lied. Let's do like an example in school. Maybe the professor says, as long as you hand in something for that assignment, I'll give you a passing grade. Trying to be nice to people, right? And you come back to him and say, how come I got an F? Well, you only handed in 3 sheets of toilet paper. How was I to give you a passing grade for that? You said that if I handed in something, I would get a grade, a passing grade. I handed in something, and you failed me. So you hear this sentence, I handed in something, and you failed me. Now, actually, I better stop this right now. I really don't recommend you adopting a threatening tone with your professors like that. It'll cause trouble. So just take this that I was trying to be funny. This is like math professor humor here. So you call out BS on an if-then by saying the if part was true and the then part wasn't. That's how you call it out. So there's a funny thing that happens if you make 2 wrongs here. If you both apply the converse and the inverse to a conditional, you get something that actually has exactly the same meaning. So it's an instance of where 2 wrongs do make a right. It's called the contrapositive. So the contrapositive of the conditional A implies B is not B implies not A. Do you see that the order of A and B has been switched, and I've thrown minus signs or negation symbols on both of them. An example of contrapositives from real life, if it just rained, the ground will be wet. And if the ground isn't wet, it didn't just rain. They actually contain the same content. 2 conditionals that are contrapositives have identical patterns of T's and F's in their truth tables. And when that happens, when you see identical patterns, the same exact sequence of T's and F's down the column in truth table, you say the things are equivalent. They're actually, if you want a better phrase, you can say logically equivalent. Often one or the other, though, if I'm now thinking about a statement and it's contrapositive, is more usable. So there's a piece of advice that you will hear. I'm going to say it to you in our next chapter. If you get stuck, try looking at the contrapositive. That's actually really good advice. So you might as well start thinking about it now. Sometimes the contrapositive will lend itself much more readily towards proving something than the original thing did. And since it's got the same meaning, why not? You can use it. Okay, so here's the truth table. We already know what the truth table is going to look like. I've already described this, but let's see how this goes. Which positions are vacuously true in the contrapositive one? Not B implies not A. The vacuous truth happens when not B is false, right? But that happens when B is true. So I'd say it's rows 1 and 3. Reveal 1 and 3. Cool. And then when is it true? Because the things on both sides of it are true. That's true down here in the bottom row, because when A and B are both false, then not B and not A are both true. So bottom row is that. And then it's easy to fill in the last position, isn't it? It's a conditional. So you're going to get an F there. They always have 3 T's and 1 F. Even if, depending on where you've put the negation symbols, you may see them in different orders, but it'll always be 3 T's and 1 F. Okay, so then we're going to we're going to be done here very shortly. The last thing I need to look at is the relationships between these related logical sentences that we've been discussing. So to do that, I want to look at table 2.1 in the General Introduction to the Art of Math. It's right here. And all 4 sentences that we're used to are in this little table. The original sentence, A implies B, is up there in the upper left, and its contrapositive, not B implies not A, is in the bottom right. The converse of the first guy is just switching A and B, right? So that's B implies A, and the inverse is the one where we left the order alone, but we put the negation symbols on it. So that one's the inverse. But you notice these decorations outside of the table. It's actually true. Excuse me. That as you move across the table, you go to the converse of something. So A implies B's converse is B implies A, but also the converse of not A implies not B is also that switch the things on either side of the arrow, right? Or alternatively, reverse the arrow. So converses across the rows and then inverses across the columns. This is A implies B, and that's its inverse. This is the converse of A implies B, and this is the inverse of that guy, the converse. You can think about the contrapositive. It's sort of interesting that if you take the converse and then take the inverse, it's the same thing as if you take the inverse and then take the converse. I suppose that makes sense. And those are the 2 changes that end up sort of canceling one another. So which statements on this page will have exactly the same truth values? We've already kind of noticed that A implies B and not B implies not A have that same pattern. They go true, false, true, true. And I don't know if you picked it up while we were doing the truth tables for the conditional, or the converse, sorry, and the inverse, but they have the same pattern too. It's just not the same pattern as these guys have. So things that are across the diagonals of this table are equivalent to one another. The converse and the inverse have the same meaning. They have the same, logical outputs, but they seem different, just as the original statement and its contrapositive seem different. So you could sometimes, no, if you had B implies A, I would still call this one the contrapositive of it. So these pairs across the diagonal are contrapositives of one another. All right. The last thing in the slides is just a piece of advice, which is that people tend to think about if-then statements in terms of one thing making another thing happen. That is, you think about the flow of time. If you light the fuse, then the firecracker is going to go off. Well, maybe not. What if it's a dud? But you might think that that's the case. If you light the fuse, the firecracker will go off. But a lot of things that we deal with in math, they don't have that sort of flow of time business to deal with them. They're just independent statements about numbers or whatever. They have no time dependency at all, maybe amongst them. So don't necessarily, zone in on the idea of causality. It can just be this one's true whenever that one's true, and false whenever that one's false. Great, now they're biconditionally connected, and I don't need to think about causation. All right, well, that's a wrap for today. Thanks for your attention, and hopefully I'll see you next time. Have a great day.